Hey all, Dr. Retzek here with you again. First of all, congratulations. You are done with section 6A. And 6A was all about getting our bearings in an inner product space, learning properties of inner products, and also nice geometrical aspects of inner product spaces by thinking about norms induced by inner products. So we got the basics down now, and we can start thinking about why one would like to do linear algebra inside an inner product space. So this is the first of a good few videos on section 6b. So here we go, section 6b. Section 6b is all about what are called orthonormal bases. So that's a new vocabulary word, actually, orthonormal. And in this short intro video, we just want to start to get our bearings on what is an orthonormal set. Okay, so think about where we are. This is all happening in an inner product space, which you guys recognize as just some vector space with a bunch of stuff in it that's equipped with an inner product. So this is a vector space like any other. It's got an additive identity. It's got a bunch of stuff in there. You're allowed to add if you feel like it. You're allowed to scalar multiply. It's just a good old standard vector space, but it's equipped with an inner product, which means it also comes with a norm, which means it comes with all that stuff about orthogonality, Pythagorean theorem, orthogonal decompositions, Cauchy-Schwarz, triangle inequality, all that good geometrical stuff that we've been learning. This setting has it. Okay. Certain collections of vectors inside this box are particularly appealing. And it leads to our first definition in 6b. Definition: a list E1 through EM of vectors in V is called orthonormal. Orthonormal, that's the term we're defining. If, well, a couple things, it's easy to say in words. Thing one, every one of the vectors on the list has to be norm 1. They're all unit vectors. They all have norm 1. Thing two, each vector on the list is orthogonal to each of the other vectors on the list, meaning when you take the inner product of one of these with another one of these, you get 0. And you can really shorten up that definition considerably by just saying that the list is called orthonormal if the inner product of EJ with EK comes out to 1 if J and K are the same, and 0 if J and K are different. So any two distinct ones of these, you inner product them, you get 0. You inner product any one of these with itself, and you get 1. Therefore, the norm is 1. So, the question is, are there any such marvelous lists sitting inside V? Are we certain that we can even find an E2, E1, E2, all the way through EM hiding in there so that that list is orthonormal? This is a big question in 6b, and it's going to take us a few days to start thinking about the question. Today, all we want to do is start recognizing how nice orthonormal lists are, if there are any in there to be found. All right, so let's think about fantastic properties of orthonormal lists. So here's a proposition. Linear combinations of orthonormal, I'm going to go with ON instead of writing that word every time. Linear combinations of ON vectors are easy to understand. And mathematically, what I mean by this proposition is, if you were interested in the norm of a linear combination of orthonormal vectors, E1 through EM, the square of the norm of that linear combination, so nice. You just pick out all those coefficients, look at the squares of their absolute values, and add them up. So absolute A1 squared plus absolute A2 squared plus ... absolute AM minus 1 squared plus absolute AM squared. So clean, so nice. So if you're working with a linear combination of orthonormal vectors, it's easy to tell what the norm of that linear combination vector is. You just read it directly off of those coefficients. And the reason this is true and straightforward, you can read the proof in this section, but basically what you got here is, look at the first m minus 1 of those in the linear combination, plus the last one. So what you have there is norm squared of green plus orange. But green and orange are orthogonal. So by Pythagorean theorem, the norm squared of green and orange is norm squared green plus norm squared orange. And then you do that again on norm squared green, and you break it down until you just have the norms of all the individual pieces. But again, those are easy because the norms of all the vectors E1 through EM are 1. That means the norm of, say, AM, EM is just absolute AM. So this is just Pythagorean theorem over and over and over again. You guys can check it out. This right here is Pythagorean theorem over and over again. And really the most important thing is that you believe this easy way to see the norm of a linear combination. Okay, so that's one nice thing about an orthonormal list. Next thing, got another proposition. That's not the only way in which orthonormal lists are nice. Next one, every ON list is Li. Li is short in our class for linearly independent. Okay, so you got to step back for a sec, make sure you're down with your 306 concepts. A list of vectors in a vector space is linearly independent if the only combination of them that comes out to 0 is the cheesy combination where all the coefficients are 0. So linearly independent means there's only one way to write 0, the cheesy way. Alternatively, linearly independent means no one of them is in the span of the others. This proposition says if your list is orthonormal, then it's Li, which is fantastic. Li lists are great. Okay, think about the proof of this. The proof of this is a direct corollary of the previous proposition. Proof. Say you had a linear combination of an orthonormal list come out to 0. Okay, well hang on then. Then 0 would be the square of the norm of that linear combination. After all, the linear combination is 0. But by the previous proposition, we know the square of the norm of that linear combination is just absolute a1 squared plus ... absolute am squared. So that means all the a's had to be 0. Thus, a1 equals ... all the way through am. Those are all equal to 0, the number. Because that's the only way the sum of the squares of their absolute values could be 0. So E1 through EM are linearly independent. And that's it. So every orthonormal list is linearly independent. Great to know. Okay. All right, let's take this up a notch. So you have this big box full of stuff. If you have an orthonormal list in there, you know it's linearly independent. If you have an orthonormal list in there of length, dimension v, not only is it linearly independent, but it's also spanning, because you guys know linearly independent lists of length equal to the dimension of the space are actually bases. So an orthonormal basis is an orthonormal list that happens to be a basis. And that leads to our next definition. An orthonormal basis. So that's the term we're defining. Orthonormal basis is an orthonormal list of vectors that is also a basis. And man, if you have your hands on an orthonormal basis, you are in business as far as studying that inner product space. And the first sort of main sense in which you love to work with an orthonormal basis is the following theorem. If E1 through En is an orthonormal basis for V, then for each vector little v in big V, little v is equal to, all right, pause for a sec. Just by virtue of being a basis, you know that each vector, little v, is a linear combination of E1 through En. That's what it means to be a basis. It's a linearly independent spanning set. So every vector in the box is a combination of E1 through En, just by virtue of E1 through En being a basis. Now, if that's all you knew, just that E1 through En were a basis, finding the linear combination of them that comes out to a given vector v is not always easy. It might be tantamount to solving some somewhat large system of equations. This theorem is telling you, yeah, that's true, yeah. Oh, but if your basis is also orthonormal, then it is not hard. And any V is simply this combination of E1 through En. So let's really read this. Think about this, what this is saying. It says, okay, here's an orthonormal basis, E1 through En. Now here's some random vector V. Right off the bat, you know V has to be a combination of E1 through En. This theorem's telling you what combination of E1 through En. So if someone hands you a random vector V, you just do V's inner product with E1. That comes out to some number. Slap that down in front of E1. You just do V's inner product with E2. Slap that down in front of E2. You just do V's inner product with En. Slap that down in front of En. And you have magically found the linear combination of E1 through En that comes out to V. It's a beautiful theorem, and it really sort of vindicates the work we went in and put in 6a as far as thinking about inner product spaces and trying to come up with an orthonormal basis, because once you do, it's just so easy to write arbitrary vectors as linear combinations of that basis. And the proof of this is just silly. So here's the proof. It's almost as though we kind of like rigged all of this to be super easy. The hard work is paying off here already just in week 2. All right, here's the proof. Well, surely V is some kind of combination of E1 through En. We know that. They're a basis after all. We're just wondering, yeah, but who's playing the role of A1? Who's playing the role of A2, etc.? Check this out. But then V, inner product with E1. Okay, so V is all this. That's what's here in that first slot. You got additivity and homogeneity in that first slot, so break it into a bunch of inner products. But all those inner products you break it into are inner products of E1, E2, En with E1. And the only one of those that survives, since all the E's are mutually orthogonal, is E1 with itself. But since all the E's are norm 1, E1 with itself, that's just 1. And therefore, this giant inner product is not so giant at all. The inner product of V with E1 is A1. Similarly, the inner product V with any of the EJ is AJ. And that's true for each J. 1 to N. And that's what the theorem says. So zoom out. We just discovered if you are so lucky to have in your hands an orthonormal basis, then the task of expressing an arbitrary vector as a linear combination of that basis is no task at all. What linear combination? This linear combination right here. So orthonormal bases are great. This immediately brings up the big question. Wait, do we know there's an orthonormal basis? Do we have one? Because if we do, that's awesome. Yeah, we do. But it takes a little work. And that's the topic of the next video and the next section of reading in section 6b. So this gets you all the way up through Tuesday. It's a little intro to 6b. Stay up on the reading and let me know if you have any questions or comments. All right, see you next time.